Hello, everyone. I'm Linfeng Zhang from Princeton, and uh, it's a great pleasure for me to give this talk on behalf of Professor Weinan Yi. And this is about more about the exchange correlation potential construction with deep neural networks within the framework of generous Kongshan scheme. And this has been primarily done with Yixiao Chen, who is also a student in the at Princeton, and also Han Wang. And Yixiao is also in the audience, so for any question, he can also answer. Okay, so I would also like to thank the organizers and also Professor Clearenberg and Marivi, who has already mentioned quite a few motivations for this kind of work. And so I will focus on here, this methodology part, because we really found that after careful thinking about all these possible ways to do this model, there are tricky problems, like how we represent the model accurately and in a transferable way. And also like when we have densities, forces, and energies simultaneously, and we want our model to produce them all correctly, how we do this optimization. And this is exactly what has been raised by Professor Clearenberg in Marivi's talk. Okay, so let's start from the introduction. And I think this is already mentioned several times, that we have this dilemma of accuracy and efficiency when we do multi-scale molecular modeling problems. And going from quantum chemistry methods, we have these very accurate methods like CCDT, and then we have lower level ones like DFT, and then we have some empirical potentials for molecular dynamic studies. And going from this highest level to here, the accuracy is typically going down, but this efficiency is going up. And as already mentioned by Professor Carr this morning, that this PES, potential energy surface model with DFT accuracy has been the major topic of my thesis work. So within the DeepMD approach, it seems that we have found a systematic way of learning data from DFT calculations and boost the accuracy of DFT with the efficiency of empirical potentials. But the problem is that still we want to have a DFT model or DFT functional with quantum chemistry accuracy to bridge the gap. The motivation, I would say there are several motivations, but the most essential one is that the data required for a PES is still very large, and we cannot produce golden standard data like CCDT for training a deep potential model. So we want these DFT models to bridge the gap. So this will be the topic of this work. And there are several related works. In particular, there are two more in the post-Hartree-Fock approach, where the other one is in the framework of density functional theory. And this has been introduced by Marivi, and also this is a work in the Tom Miller group. Okay, then let's go to see how we approach this problem. Okay, so what's essentially required is a reduced self-consistent model that produce energy, forces, and like charge densities. But we want to understand and solve this problem in two steps. The first one is, it's more like a post-Hartree-Fock approach. When we have a solution like from Hartree-Fock or Kongshan approaches, what we have is these single particle orbitals and the energies. And we want to see what's a correlation energy or what's a correction of these Hartree-Fock or Kongshan energies compared with the ground truth. And this is a correlation energy. And this correlation energy in general is a function of these Hartree-Fock or Kohn-Sham orbitals. And when we have a good understanding of this energy model, we want to make it self-consistent so that these orbitals and these corrections could be introduced in a self-consistent loop. And then we will have these energies as a minimum of this of the energy functional to be minimized. And simultaneously, we will not only have energies, but also by Hellman-Feynman, we will have forces, and also we'll have these charge densities. Presumably, if we have the correct model, these quantities will be correct. So then there are several challenges. So I will summarize them into 3 categories. One is how we represent the model. So we need principles to be followed. And in particular, we have already know quite a lot, like how we follow, like satisfy physical constraints and follow the Jacob's ladder to make the functional more and more accurate. And we also have these expansion approaches based on couple clusters and configuration interaction and so forth after the Hartree-Fock approach. And that's how we represent the model. And second one is data is now really expensive because we are not solving the Schrodinger equation directly in this approach, but we need data to train our model. But it's data is very expensive, so generation of data should be very adaptive and also careful. And finally, how we do the optimization. In particular, if forces and densities are properties at the minimizing orbitals of the self-consistent loop, how we introduce them in our training approach. A direct or straightforward way to introduce them will cause, if we want to use a first order method to do the optimization, we need these gradients of density with respect to the parameters we introduce. That will be a very expensive task. But if we don't have that, how we do this optimization? So these are the challenges. Okay, so then let's start from how we construct the model. We view these following properties to be important when we consider how we do this model. The first one is universality. Here we are relatively conservative, so we are not targeting at a true universality, but we want to have a universal model for which we have data so that we can test this universality. And I will just explain a bit better later. And second one is locality. Locality is also a very tricky and idea, but here our target is to learn from small systems and extend to larger ones, so that we want to learning object has to be in a small input domain, so that after learning we can transfer to larger systems. And there are important symmetry requirements to be satisfied. Here, not only rotation, translation, permutation, but also for a self-consistent model, we need this gauge invariance. And we want it definitely to be much accurate at the compared with expensive models, but also efficient and comparable with DFT and Hartree-Fock schemes. That's our requirements. Okay, so and then after all these requirements, we will start from this energy model, which take Hartree-Fock or Kohn-Sham orbitals as input and target at correcting this correlation energy. So how we construct this model following the previously mentioned criterions, that seems to be the key step. What we found to be a fairly good starting point is actually the single particle density matrix, which is this guy because naturally it satisfies this gauge invariance, and also it's fairly local for many systems. And also it's a universal functional of the correlation energy. But how we represent, but what we target at is the functional, which will still be taking an infinite number of degree freedom if we take this directly into our model. So we have to do some sort of projection. And here we project these orbitals onto atomic bases. And also this basis is not dependent on atomic species, so that we want this to be transferable among different species, like what a quantum chemistry method does. And after this projection, we can probably think that if the basis is close to complete, then this still faithfully represent is the information contained by the orbitals. The full information is then here. So we do this expansion, but it do has several non-diagonal component here. This atom index I, and radial part index, which is N, and this angular index, which is L, and this M, which is associated with each L. Now this is the full information we are gonna deal with, and this turns these orbitals to numbers. But this is still a very large matrix, and we want to make it local and extensive. How we do this? So the most straightforward, as already asked in previous questions, is just to take the diagonal part of these projections. So by doing that, we have this diagonal part in the direction of the atomic species and atomic indices, and also angular and radial part. But we have this M associated to L, which will be covariant upon rotation. So we have to fix this covariance of this local density matrix. So here we take the eigenvalues of these M's, so that this will become rotationally invariant. And after having these rotationally invariant features, we fit it into a fitting function. It could be neural networks, and it could be linear regulators if that's already good enough. But this is a general fitting function. And extensive property will be guaranteed because this is a summation of the function of atomic contributions, and atomic descriptors are these D's. So when we have trained the model from small systems, when we apply it to larger ones, we can naturally take this D to calculate this D on several different atoms and scale it up in a straightforward fashion. So that's how we construct these models following the previous mentioned requirements. And definitely if the locality, if we in practice, the local input here is not enough, we can still have several extensions. The most straightforward two and natural two are, first one, add some operators onto the density matrix, which for here we can ask the Fock operator here and take optical energies into account. And this will define our extended descriptor. And if we want to add some sort of non-local information, like here, we do have this density matrix in the diagonal, off-diagonal part in the direction of atom indices. So we can do this. And by summing up contributions from neighboring atoms J to atom I, so that we will have a more non-local descriptor. And after we have this descriptor, we can still fit it into a nonlinear function to define the energy contributions. And actually, this is also a similar idea has been also used in the deep potential approach. Okay, so this is how we construct our model. And when we turn our model into a self-consistent loop, what we are essentially doing is that we are not actually dealing with the minimization problems with respect to the density matrices, but we are still doing this with respect to orbitals. So actually orbitals are the building blocks of the functional dependence. So this is well suited for the generalized Kongsham approach. And so the minimization problem is straightforward. We have this correction term, which is also functional of orbitals. So we can definitely do this functional derivative and then define this self-consistent loop. And that will define our self-consistent model. And this is our modified self-consistent field equation. Okay, but the hard part is actually, as I mentioned, is the training part. Okay, so first of all, here is still, for the energy model, it's straightforward to do the training because for each molecule, we do this Hartree-Fock calculation and we calculate the descriptors, and then we will have the energy as target, and we have the parameterized neural networks or linear parameters, and then we do the optimization. That's relatively straightforward. But here, the subtlety introduced by this self-consistent field is that our we care about is not this functional dependence, but the minimizing values of this functional dependence. What we care about is actually the arguments of these orbitals, and observables as a function of these orbitals, like energies, forces, and densities. So then, actually, to train the model, the difference is to train the energy model, it's straightforward because this model is defined as descriptors, and we directly do the minimization with respect to the parameters. But when we train the self-consistent model, within this, whenever the parameter change, the functional dependence changes, and the energy will change. And we have to do an additional minimization procedure with respect to the orbitals, which will be very expensive. And that's only for the energy. So how do we do this? And actually, it's already, the strategy is already mentioned and introduced by Marivi and in this neural XC scheme, which is we actually just switch the order we do the optimization. Here we reformulate the training procedure into a constraint optimization problem in which for each fixed orbital, we minimize the parameters. And that's the outer loop. Now that's the inner loop. And after we minimize the parameters to the solution constrained at this orbital, we do a minimization over this orbital space, so that this iterative approach will go on until the convergence, in which actually this energy model will become self-consistent model. And that's how we optimize the energy. And actually, this is also adopted by NeuralXC. A slightly different part is we always use a neural network, a single neural network or single linear model to play the role of the fitting function, but they seem to add one layer after each iteration. Okay, so this is a schematic illustration of this approach. So a direct relaxation process is more like the original one, so the orange one, which just always go along the argmin of a functional dependence and ultimately reaches this ground truth solution. And for this green curve, it just do a very large step in the parameter space and then just goes back after a CF. And typically what we observe is a few numbers of iteration will just reach convergence of the model. Okay, so then after this outer loop, how we introduce forces as training input. Forces, if we have this self-consistent model, it's natural to use Hellman-Feynman's theorem to produce these forces. And that seems to be straightforward. But when we introduce forces in the training, in the loss function, it has parameter dependence, so that we actually, when we do first order minimization problem, we actually need one more derivative, which is a derivative of the model partial E over partial X, and then this guy, partial this guy over partial parameters. And that's in general requires things like DFPT calculations, which is very expensive. But here, actually, there's one more trick for which this part which play the role of a correction is the part that depend on the parameters. And it's very interesting that this part can be still naturally written as a very efficient evaluation of the output of the self-consistent solution. So this can still be introduced in the training scheme. And then the next one, how we use density as labels. Actually, there's two straightforward approaches which are tricky. One is just to define the loss function in the, to introduce the density in the loss function. The other one is just like what Marivi has mentioned. We can just, for each density, we solve an inverse problem to obtain the potential, and we use potentials, which could be like up to a constant to play the role of the target, so that we can do the optimization. But either way are very expensive, and we don't know like how we balance these things with energy and forces. So it seems to be hard to adopt them. And essentially, there's another work by a Japanese group, which actually use Monte Carlo schemes to optimize neural networks to match the densities, which seems to be a sacrifice of efficiency due to these hard problems. So how we view this, how we address this problem, and this seems to be the interesting part, because like 2 years ago, there's a science paper by Purdue co-workers that observing that density functionals is straying away from the path towards the exact functional, because some of the density functionals give consistently right energies and consistently good energies and densities, but at it's proceeding slowly. But the other type of functionals are more accurate for energies, but stray away in the direction of density. So how we, turning that into a learning problem, it means how we optimize energy and densities together, given we have a well-defined functional dependence and we have a list of parameters. Okay, here, what's in our, actually our proposal is to not introduce densities into the loss functions, but introduce densities into the self-consistent field, which is what we do is not here is what we, our self-consistent model. And in our minimization problem, we can define one additional term. We can call it penalty term, whose strength is given by lambda. And this term measures the difference of the current density and the density labels. And you can see that this term is actually quadratic with respect to the density. And also, it's as a function of the penalty, it's actually a non-decreasing function of lambda, so that only this density and energies match exactly to the data. All this E lambda become equal. So then for different lambda, for the right model, all these energies should match the label, but for a model that has wrong density, it will have two different energies. This will be a signal that we are doing things wrong in the density direction. So actually, and also this can be directly evaluated as an additional potential term. In this way, we do introduce density dependence in our optimization procedure, but the loss function is still like a function of energies. Okay, these are our strategies to do an optimization for energy, forces, and densities. And the last issue, as I mentioned, is optimization procedure for machine learning problem also require data. And data is in particular very expensive for a model targeting at chemical accuracy. So here what we can use is actually also widely adopted idea in the field of constructing the potential energy surface is an active learning procedure. Given the set of data we have, we don't evaluate all these accurate energies for all this data, but we use an iterative approach in which we just use part of the data to do the training, but we train several models, and we use this disagreement of several models to decide what are the next set of data we put for accurate calculations. And then we improve the model in an iterative way. And this is the active learning idea. And actually, to put it further, if we do have a model to run dynamics, we can even use a model to explore the chemical or configuration space. And that we call it a concurrent learning scheme. So with this active learning scheme, we have introduced all these procedures for our method, which is a construction of a good model, and then this optimization strategy for a self-consistent model, and then this active learning approach for data generation. And then let's have some short discussion of the results. Okay, so as I already mentioned, the hardest part for validating and for doing these methodologies are how we choose data. And it seems that what we have right now playing the role of like benchmark data set are two. One is this QM7BT data set, which contains several thousands of molecules, but which only has energies, CZDT energies, but no forces. But the reason we choose this data set is that at least it contains a lot of different molecules. And the other one is a recent one used by the GDML approach, which has thousands of configurations for this MDA molecule. And it contains both CZDT energies and forces. And actually, we also did density calculation for these configurations so that we can also train for energy and densities for these configurations. So these are the data sets we use for testing our proposed approach. And some of the computational detail, we use PySF and this atomic basis to do all these calculations. And the projection basis are the Gaussian type orbitals. And in particular, this basis set is not dependent on atomic species. And this is a difference between this procedure with and the NeurXC procedure. And the fitting functions, we actually used both neural networks. And for simple problems, we also tested the performance of linear models. Okay, with these details of the model, let's see how it performs. And okay, so this is the first result, the performance of the energy model using the linear fitting function and the basic neural network fitting function. And also these two are using extended descriptors. And as we can see, this is a prediction accuracy versus the number of training samples plotted in the log scale. So this is typically called the learning curve. And as we can see, as the training sample increases, a number of training sample increases, the accuracy is becoming better and better. And even the linear model actually saturates below the chemical accuracy. And when we introduce neural networks, it just goes down pretty quickly. And as a benchmark data set, we compare with this MOB-ML, which use kernel method and other descriptors. And so, which seem to have a larger prediction error. So this is a energy model we tested on the QM7BT data set. And then let's say how we do active learning. So by active learning, we are no longer just using this data set randomly, but we just increase the set of training data in a systematic way. So starting from also 1,000 data, if we use active learning, so the data required is essentially what we need. So the improvement of accuracy will just become faster. And because the testing data is only 7,000, we can only show this improvement at this level. But I believe for larger system size, for larger amount of data, this will be a very important step to realize a truly generalizable model. Okay, and also when we prepare this work, we found some larger data sets. So we also perform a test based on this larger data set. And this data set is called ANI1 CSX, which gives actually some linearized CZDT based energies for a much larger data set. And after this training, its testing data is very different from the training data, which has this reaction energy benchmark HC7 11, and also this isomerization energy, this so-called ISOL6. And this deep post-country fork methodology gives consistently good results. Okay, and this figure is to show that after we make this model self-consistent, we don't lose accuracy. And essentially, we have also equally good energies when we use this self-consistent model for energies and also use this iterative training procedure. And then last, we introduced the forces in our training process. And it's interesting to observe that after we include forces, we have definitely performed a much better performance in terms of both energy and forces. And in particular, what's interesting is that when we compare this with our potential energy model, DeepMD, you can see this training curve is much below this training curve of DeepMD, which means this self-consistent model is much less data demanding. This is also because it captures more physics and also it's more local. Finally, when we put density in our training, what I want to show is two numbers. And as we can see, as a comparison, we did a comparison with scan zero model, and we compared energy, forces, dipoles, and density. And it seems that with densities in the training, we can have equally good, we can have good performance in terms of both densities and energies. But if we don't have densities, we do have larger prediction error compared with scan zero. And definitely in the direction of it's measured on the density space. And definitely for energies, DeepXC gives much closer agreement with the benchmark CCSDT. And this value actually is, in practice, is smaller because currently we only use CCSD densities to do the comparison. We just finished the right density to compare with, and it seems to be even lower than this value. And
Linfeng, do you have a summary page? Yep.
Okay, yeah. So then let's go to the summary. So with this, I think I hope I can convince you that we really need to think about different perspectives when we want to develop exchange correlation models, the representation of the model, the optimization strategy, and how we generate data. And what's next? A larger system and data set, definitely. And also we want to see how it performs for extended system like in the condensed phase, and also several real-world applications. And potential difficulties are, I would say, this potential difficulty is mostly in the conceptual idea, like how this size extensive property is guaranteed or not. And also it's possibly hard to learn multi-reference systems. And ultimately our hard part is how we have good how we generate good data. And along this line, we have seen a lot of talks today introducing different ideas. So, but still, like there lacks a systematic approach like DFT to give us data labels. And this approach in this direction, I believe, will just push this field a large step. And with this, I finished my talk, and this is my acknowledgements. And thank you.